Hi, everybody. I know that Miss Kennedy went over problems from 6.10 up to problem number 10. She did 1 through 9. She told me she did not do number 10 through the end. So I'm going to go ahead and do those on this short video. So this question here says the number of a certain type of bacteria present in a culture is determined by the function, and they give us the function f of x equals 2000 times 3 raised to the x power, where x is the number of days that the culture has been growing. Determine the number of bacteria present after 3 days. Okay, so we want to write our function down, which was given to us, f of x equals 2000 times 3 raised to the x power. So in this case, x is the number of days, and we were asked to find it after 5 days. So we're going to do 2000 raised to the 3 with the times 3 raised to the 5 power. So in my calculator, where am I going to start? I'm going to start with the exponent, right? So I'm going to go ahead and I'm going to put in the 3, and I'm going to raise it to the power of 5, and I get 243, and then I'm going to multiply by 2000, and the number of bacteria that I would have is quite high, 486,000 after 5 days. All right, let's go to the next one. So in this one, we have the town of Lockport currently has 4,000 residents. The expected future population can be approximated by this function. P of x equals 4,000 times 1.3 raised to the 0.1 times x, where x is the number of years in the future. First, we want to determine the expected population of Lockport in 10 years. So in that case, x is going to be equal to 10. So we're going to go ahead and write our function down. So the population, actually we should put P of 10 equals, because we're calculating it in 10 years, 4,000 times 1.3, and we're going to raise it to the 0.1 times 10. Okay, and then if I simplify that exponent, what do I have? So if I take 0.1 and I multiply by 10, I just have 1. So basically, I'm just going to have that power, that base of 1.3 by itself. So 1.3, if I raise that to the 1 power, I just get 1.3. And then I'm going to go ahead and multiply by 4,000, which was the starting population, basically. So we would expect to have 5,200 residents in 10 years, assuming that particular, sorry about that, considering that particular function. All right, so let me get back here and, oh, wrong screen. Sorry, I got all stuff messed up here. Hold on just a second. All right, and the second part of the question asks us to find the expected population of Lockport in 50 years. So we're going to evaluate the function when x equals 50. So it's the same function. And the exponent this time, I'm going to have 0.1, oops, times 50. So my exponent, that doesn't look very good, does it? It's 0.1. So I'm going to have for my exponent 4,000 times 1.3. And if I take 0.1 and I multiply it, so 10% of 50 is just 5. So in my calculator, I'm going to start with the exponent again. I'm going to take 1.3, raise it to the 5th power, and I get 3.71293, and then I'm going to multiply by the 4,000, which is the starting population of the town. So I get 14,851.72, which of course we would round up because we're talking about population. So we'd have 14,852 people in the town at that point. All right, so let's go on to the next ones. So on the last page of the problems that we were given in class, we've got a problem here with, we're talking about the price of an item today. P is the price of the item today. The price of the same item n years from today is going to be given by this formula. P of n years from today is equal to P, the current price, times 1 plus R, where R is a constant rate of inflation. And we want to determine the price of a movie ticket 10 years from now if the price is $8 today. So we want to do P8, all right, and the ticket price today is $8, which goes in front. And then we're going to put 1 plus, and the inflation rate that they gave us was 3%, so 1 plus 3. And we're going to do that as a decimal. Yeah, we're going to change this to the decimal. Let me apologize. Let me rewrite this again. You have to change that just like we did with our consumer math problems. We have to change that rate to a decimal, so 0.03, and we're going to raise that to the n power, which is 8 years. So we've got 8 times 1.03 raised to the 8th power. So this is basically like you were doing with your consumer math problems. So you're going to take 1.03 exponent to the 8th power. Oh, 10 years. I'm sorry. I'm doing the wrong number of years. Let me go back for a second. This was 10 years. 10. Sorry about that. The ticket price started at $8. I was thinking, why would I give you 2 8s in a problem? It should be 10. Let's go back. So I'm going to take 1.03 and I'm going to raise it to the 10th power because I'm going out 10 years. And then I'm going to multiply by the current ticket price, which is $8. And I get, well, that's not right. Let's try it again. 1.03 raised to the 10th power. There we go. Times the current ticket price, which is $8. So the ticket price in 10 years would be $10.75, assuming that function actually models what is going on with the price of items in the future. Okay. Here's another one. So suppose that the sales in units of a new product brand XYZ are described by the function S of t, the sales of t, 4527 times 0.5 raised to the t power, where t is the number of years after the first year of introduction. All right, so determine the sales 3 years after the product was introduced. How much sales are lost each year? All right, so we've got our function here, and we want to figure out where it's going to be in 3 years. So we want to do S of 3. So we've got 4527 times 0.5 raised to the 3rd power. All right, so let's go ahead and do that in our calculator. So we're going to take the 0.5, always do the exponent first, raised to the 3rd power, and then we're going to multiply by 4527. So we expect the sales to be 565 point, that I have on my calculator, 0.875. 875. And let's see, is that actual sales? Yeah, so that's actual sales. So we actually should round this off because these are actual units. So you want to go ahead and round this off to 566. These are sales, so these are actual units. And then the second part of the question said, how much sales are being lost each year? So if you go back and look at the way we set up exponential functions, right here tells you what's happening here. So every year that goes by, you're losing 50% of the sales. Okay, because you're only multiplying, and multiplier here is 50%. So you're saying every year that goes by, I'm losing 50% of my sales. So over 3 years, I've gone down 50% in 1 year, and then 50% again in the next year, and 50% again, and we end up at 566. So 50%, and that's coming from the quantity in here. Because it's less than 1, we know that this is like a decay function. Okay, so these here now are going to be using the base E, which is a really important base in many science applications. So we're talking about a population of a country. It's about 1.31 billion people. Assume the population continues to grow exponentially at this growth rate, 0.07 per year. The expected population of the country in billions t years after this year is given by this function. And notice the base here, instead of having a number base, it is a number, but it's a special base called base E. We want to find the expected population in the country after 4 years. So we want to find P of 4, which is going to be equal to 1.3 E, and we're going to raise that to 0.007 times the time, and our time we want it was 4 years. Okay, so the first thing I'm going to do is simplify my exponent. I'm going to take 0.007 and I'm going to multiply that by 4. And I get 0.028. So my exponent here is going to be 0.028. Okay, so what we're going to do now is, all right, so I'm going to show you on the TI-30XA calculator. So right here is your e to the x key here. And I have to remember how to actually do it. It's a second function, and I believe I put the x in first. Let's take a look and see. So let's put in the 0.028, and then I believe I hit that key. Yes. Okay, so on this calculator, you're going to put in the value for x, whatever the exponent is, and then you're going to hit second, and then that'll get you the second function on the ln key, and that's going to bring up that base e, and it's going to raise base e to that power. Okay. Let me stop for a minute just to make sure. Oh, I did it again. Okay, hold on just a second. Okay, and now, so now I've simplified this part here, and then I'm going to multiply by 1.31, and I get an answer of 0.785. All right, let me go back for a second because something I did wrong here. That answer should be greater than the 1.31. So let's go back again and do it. So 0.028. Okay, and then I'm going to hit the second key, e to the x. So I've got 1.028, and then I'm going to multiply this by 1.31. There we go. That makes more sense. I don't know what I did before, but it wasn't right. 1.3, 1.347, and this was in billions of people. Okay, and the reason I knew it couldn't have been right was because the number I was multiplying by here was greater than 1, so I knew it had to be greater than what I had over here, which was 1.31. So we're up to 1.347 billion people. And by the way, if your calculator does not have an e to the x key, let me show you a little thing you could do here. So on this calculator, let me just show you what base e is equal to. So any base raised to the 1 power gives us the base back. So base e, in case you don't have an E key on your calculator, E is going to be approximately 2.71828. That should be fine to use as an approximation. So if you don't have an E key on your calculator, instead of looking for that, you could substitute 2.71828 for E, and then we'll get to a close enough answer because we're rounding these off. All right, let's do another one that has base E in it. So this time we have radioactive material decays exponentially, so we know we're going to get a number lower at a rate of 2.54% per year. The amount of radioactive material left Y after T years can be found by this formula, where Y naught is the original amount of material. So if we start with 6 grams, how much will be left after 60 years? So we want to find the amount after 60 years. And we started with 6 grams, and then we have E, and we're going to raise it to the negative 0.0254 and times T. Oops. Times T, and my T here is 60. Okay, so the first thing I'm going to do is I'm going to simplify my exponent, and remember, this is a negative exponent, very, very important because this is a decay function. So I've got negative 0.0254 negative times 60. So I get negative 1.54. Okay, so I've simplified that part. Okay, so now what I'm going to do is I'm going to take that number's already in my calculator, which is really nice for me. What I'm going to do now is I'm going to hit second e to the x. So now I've simplified this part here, and then I'm going to multiply by 6. So after 60 years, there's going to be 1.307 grams of material left, which again makes sense because I know that this is decaying, so therefore I expect to have less. So again, if I don't have an e to the x key on my calculator, I can use this right here as an approximation. And just real quickly, let me show you on the TI 8384 where the e to the x. Okay, so if you're using the TI, this happens to be an 84, but they're going to be in the same position. They're going to be right over here above the ln key, same way, and it's going to be second ln x. Remember, on this calculator, you need to make the numbers negative before you put them in, and there's your negative sign right there. Okay, so let's do this one, for instance, right here. We'll do this problem here. Let's turn the calculator on. All right, and I don't know if I can get this all in at once. So first thing I'm going to do is I'm going to put in the negative 1.54. So I go put negative 1.524. Bring it down so you can see it. There it is. Now, the problem here also is I need on this calculator to hit this function first. So let's go back. Let me scroll back here. I can actually do a second insert. I can actually insert the function in front of it. I think that's going to work. Let's try and see. So it's second ln x. Oh, it's not going to work. Okay, I'll put it now. See what happened. Let's clear this out and start again. Okay, so I'm going to do second e to the x. Okay, so there it comes up with e, and it shows it now as an exponent. And we want my exponent right there to be negative 1.524. Get my number, and then I multiply, in this case, by 6, and I get 1.307, which is what I got before. So on this calculator, it's a little tiny bit different in the sequence of putting the numbers into the calculator. So hopefully this will help you on the few problems that Miss Kennedy was not able to do in class. And again, next week at the start of class, I'll take any questions that you might have on section 6.10. So have a great week.